Hola! All right, we've come to the Physics Chapter 9 lecture, Lecture 2. On your notes, we're going to be start at the very bottom of page 2. And this is the last lecture that I will be giving you over new material before Christmas. Okay, so no new material until January, after today. All right, let's start at recoil velocity. That's the velocity an object develops in response to launching another object. So in your book, there's a picture of a rocket. I don't know how well you can see it here, but you're on page 302. And just think of that. You don't have to write this down, but if we could, that's no good. Okay, let's let me draw some kind of rocket here. Okay, so you want to launch a rocket. A rocket is actually, of course, let's say it's going up towards space. It's recoiling against its own exhaust. So its exhaust is coming out so fast, even though the exhaust isn't nearly the mass of the rocket, although it certainly does have mass. It's coming out so fast that the rocket launches in the opposite direction. So kind of like how a gun recoils the opposite direction of the bullet. Okay, so momentum is conserved here. There's no other forces acting on the system. It's just the rocket and the exhaust. All right, so open up to page 304 and we'll begin working the on your own problems. And I printed it out this time. I'm not sure if you can see this or not, but page 304 in the book says, what's the recoil velocity of a 1.21 kilogram rifle that shoots 25 gram bullets with a velocity of 195 meters per second? All right, so we're going to be using the momentum before is equal to momentum after. That's the law of momentum conservation. All right, so momentum, we'll just use a B for before, is equal to momentum after. So what that means is the mass of the gun times the velocity of the gun plus the mass of the bullet times the velocity of the bullet. This is the before situation. Has to equal the mass of the gun times the velocity of the gun plus the mass of the bullet times the velocity of the bullet. And this is the after situation. Now, is the gun and the bullet moving before you pull the trigger? No. So the before situation is just zero. There's no momentum at all. So I would have 0 is equal to the mass of the gun times the velocity of the gun plus the mass of the bullet times the velocity of the bullet. So let's pull this over to the left. I'd have minus the mass of the bullet, velocity of the bullet is equal to the mass of the gun, velocity of the gun, and then solving for velocity of the gun, it's going to be minus the mass of the bullet, velocity of the bullet, over the mass of the gun. All right, the mass of the bullet is 25 grams, so minus 0.025 kilograms. Velocity of the bullet is 195 meters a second. And then the mass of the gun is 1.21 kilograms. All right, so if you plug that in the old calculator, you get minus 4.03 meters per second. So it should make sense that it's going in the negative direction because the bullet is going in the positive direction. If the bullet was going in the negative direction, the gun would be going in the positive direction. All right, let's do another one. (9.7). So again, we're using momentum before is equal to momentum after. That problem says a 75 kilogram astronaut is making repairs on his ship in space, accidentally loses his grip. He floats away from his ship and to his horror finds that the tie line which supposedly attached him to the ship has come undone. He floats motionless in space several meters away from his ship, but being a good physicist, he realizes that if he throws the wrench, which is 1.2 kilograms, he is holding away from the ship, the law of momentum conservation says he should begin moving towards his ship. If he can throw the wrench with a velocity of 10.1 meters a second away from the ship, at what velocity will he travel back to his ship? All right. So momentum before is equal to momentum after. So the mass of the astronaut times the velocity of the astronaut plus the mass of the wrench times the velocity of the wrench. That's the before situation. Has to equal the mass of the astronaut times the velocity of the astronaut plus the mass of the wrench times the velocity of the wrench. And that is the after situation. All right, the astronaut, the wrench, he hasn't thrown it yet before. Now, it's not always going to be 0 on the left side, but these first two examples it is. All right, so I'll have 0 is equal to the mass of the astronaut, velocity of the astronaut, plus the mass of the wrench times the velocity of the wrench. We want to know the velocity of the astronaut. We're going to move this quantity to the left, so minus the mass of the wrench, velocity of the wrench is equal to the mass of the astronaut, velocity of the astronaut. Solving for velocity of the astronaut, it'll be minus the mass of the wrench, velocity of the wrench, over the mass of the astronaut. The wrench is 1.2 kilograms, so minus 1.2 kilograms. The velocity he threw it at was 10.1 meters a second. He should have thrown it a little harder. And the astronaut is 75 kilograms. Okay, so he's going to float back to his ship at minus 0.16 meters per second. If he'd thrown it a little harder, he would go back towards the ship a little faster. All right, so I hope he doesn't have to pee because it's going to be a while before he gets to his ship. All right. That's 9.7. Let's look at 9.8. So 9.8 is a little bit different. It says two figure skaters are performing a routine. The man travels towards the woman at 1.2 meters a second. The woman jumps toward him with a velocity of negative 3.1 meters a second. After the man catches the woman, at what velocity will the two skaters be traveling? All right, so this is a before and after situation. All right, so I would have the mass of the man times the velocity of the man plus the mass of the woman times the velocity of the woman. And then they're both together on the after situation. So the mass of both times the velocity of both. This time the before situation is not 0. All right, so the man is 75 kilograms. He's moving at 1.2 meters a second. The woman is 60 kilograms. She's moving in the negative direction, negative 3.1. And then I wish I'd started further to the left. The mass of both is going to be 75 plus 60, so that's 135. And we're trying to figure out the velocity. Okay, so you would have negative, if we, the left side, if you add these two together, you'll have negative 96 kilogram meters per second is equal to 135 kilograms times the velocity of both. So the velocity of both is equal to negative 96 over 135. And that's going to be negative 0.71 meters per second. All right, so that's the law of momentum conservation. And let's go to the last topic, last new topic before Christmas. All right, we're at the bottom of page 3, and we're going to talk about angular momentum. So angular momentum is momentum associated with rotational motion. If you want to look at figure 9.1 and figure 9.2 and look at that, angular velocity is the rate at which the position angle changes. So the angular momentum formula, so this is one you're going to have to memorize. All right, that is L. L stands for angular momentum. It's mass times velocity times radius. All right, so the law of angular momentum conservation is if the sum of the torques acting on a system is equal to 0, angular momentum never changes. So with angular momentum conservation, you'll have L before is equal to L after. So that's going to be mass times velocity times radius before is equal to mass times velocity times radius after. And unless the mass changes, and the mass might change, you could have a second thing added to it. But if it doesn't change, it'll end up canceling out. All right, so if we were in class, I would give you some examples. One example is a figure skater doing what's called a camel spin. You can look that up on YouTube. Just look up camel spin. When they have their arms out, they are moving slower. When they pull their arms in, they reduce the radius, and then the velocity must increase in response. A cat, when a cat falls, the way that the cat always lands on its feet is it twirls its tail, and the cat will spin in the opposite direction that it twirls its tail. Okay, so that's an example. And you can just do it in a chair at school. If you will start spinning in a chair and have your arms and legs out, and then bring your arms and legs back in, the chair will start spinning faster. I usually let people in class do that. So see if you can get a teacher to let you give that one a try. All right, let's look at 9.9. Give me just a second. There we go. All right, this is going to be hard for you to read in the video. So just look at your book on page 309. It says, in a cruel laboratory experiment, a mouse is placed near the center of a plate. So the mouse at the center of the plate, spinning freely. In an effort to get off of the plate, the mouse begins to crawl towards the plate's edge. What will happen to the speed of the plate? What will happen to the speed at which the plate is spinning as the mouse crawls in that direction? Okay, so we know that L is equal to mvr. So the radius is increasing because the mouse is moving out towards the edge of the plate. Therefore, the velocity in response, if L is going to stay the same, the velocity must decrease. All right, and finally, your last on your own before Christmas, and it's only, I think, November the 12th, so there we go. So 9.10 says, a toy similar to the one used in the example, okay, you can just look in your book in one of the blue example problems to see that, is used to get a ball spinning at a speed of 7.5 meters a second, a radius of 22 centimeters. If the string is adjusted such that the ball travels at 3.2 meters a second, all right, so the string is slowing down, right? What will be the radius of motion? All right, so we're going to have angular momentum before, so mvr before has to equal mvr after. All right, now in this particular case, the mass doesn't change. I think there's a homework problem where it does, okay? So if it doesn't change, you can cross them out. We want to know what is the new radius, all right? So radius after is going to be velocity times radius before over velocity after. I could use 1 and 2, probably other teachers would. I think before and after, though, gives a little more description. So 7.5 meters per second is what it started out at. Sorry about how messy I'm going to be writing this, but I'm reaching around a music stand. 0.22 meters is the original radius. And we have 3.2 meters per second is what it slowed down to. So that is 0.52 meters. So we increased the radius and the velocity ended up slowing down from 7.5 to 3.2. All right, that does it. You will get a solutions video for Chapter 9. That'll be your next video so you can check your homework. The homework is... All right, and is on, I am still keeping the physics schedule on my Weebly website. But a lot of my classes I'm not. You can also look at the assignments on MS Teams, and in the description of the assignment it says what your assignment is. But you're going to be doing review questions, page 315. Finish those up. That's 8 through 10. And then practice problems, page 316. You'll be doing 5 through 10 on that. So I will talk to you on the Chapter 9 Solutions video, and have a good rest of your day.